So good morning, everyone, and welcome to this EURASIP webinar. I'm Emanuele Magliarana. I'm the chair of the Biometrics, Data Forensic, and Security Technical Area Committee of the EURASIP. This TSC focuses on several aspects of digital security, such as data forensics, covert communications, biometric recognition, multimedia, physical layer, and network security, and so on. And this webinar today will be given by Aleksandra Mileva, which is full professor at the Faculty of Computer Science, Goethe University in SIP in North Macedonia, where she is also the head of the Laboratory of Computer Security and Computer Forensics. Her research interests include computer and network security, digital steganography, IoT protocols, and information security, cryptography, computer forensics, and quasi-groups theory. Aleksandra is currently the conference chair of the forthcoming European Interdisciplinary Cybersecurity Conference in 2023. She is a member of the editorial boards of Journal of Cybersecurity and Mobility, Frontiers in Computer Science and Mathematics, Computer Science and Education. And last but not least, Aleksandra is a member of the EURASIP B4SEC TSC since 2019. So this webinar is entitled DICOM Standard, What We Know About Its Security, and is about the security issues concerning the digital imaging and communication in medicine standard, which currently is the most employed framework for representing, processing, transferring, storing, and displaying medical imaging data. So for the audience, first of all, thank you for being here. If you have any question following the webinar, please write them in the chat. So at the end of the webinar, we can ask your questions to Aleksandra. So thanks a lot, Aleksandra, also for being here. And I can leave the screen for you.
Okay, thank you, Emanuele, for the nice introduction. Hello to everybody. First, I would like to also thank EURASIP people because they made this to happen. And also it is nice to be here and give this talk about the DICOM standard and its security. Here is outline of my talk. So first I'm going to speak about the motivation for the subject and why we chose it for our research. Next, you will have a crash course in DICOM because I think you need to know some little DICOM basics and also to observe its complexity before we go to the next step and speak about its security. I want to make clear here that I'm not expert in DICOM standard. I only know DICOM so much so I can research about it. After the crash course, I will present something about possible attacks in DICOM, and at the end I will speak about security features which are built in DICOM standard. Some of the figures and examples in this talk, those from DICOM Basics, but also about information hiding in DICOM and zip bombing, are from 2 our papers and 1 poster, which are a joint work with Luca Caviglione, Alexander Velinov, Stefan Wenzel, and Vesna Dimitrova. So now I will start with the talk. We are witnessing many attacks on medical institutions and healthcare systems, and one of the most serious threats today is ransomware, because due to this attack, hospitals cannot function normally. Their computer systems are down. Some hospitals were closed for several days or weeks. Patients cannot obtain their treatment and care, and even their life is threatened. For example, in my country, a health insurance fund of Republic Macedonia was a victim of a ransomware attack in February this year, and many people didn't manage to use their insurance for healthcare treatment, and also health workers in the state hospitals couldn't get paid for weeks. Another very serious threat to healthcare sector is data breaches with exposed of millions patient data and also customer data for health insurance companies. Then we have insider threat, distributed denial of service attacks, and similar. Also, there are many cases in research how different medical devices like infusion pumps and pacemakers are easy to hack, and how they could be lethal in hands of hackers. To see how big the problem is, I will give a little bit statistics. So you can see here from the IBM report from 2022, the average cost of a healthcare breach in 2022 was $10.1 million. And this is approximately 2 to 5 times higher than the cost in any other industry or sector. Also, from the Verizon report, you can see that there are 849 incidents, and in many of them, the threat actor was internal threat actor in 39% of the cases. Next, I will start with the DICOM. One of the most important medical standards is digital imaging and communication in medicine, or DICOM standard, which provides a framework for the diagnostically accurate representation, processing, transfer, storage, and display of medical imaging data. This is a very big and very complex standard. It has more than 7,000 pages, and also it is divided in 22 parts, which are constantly changing. Also, there is a special DICOM standard browser from different companies, like for example from Monolithics, which you can use if you want to research about DICOM, to browse the standard and similar. I will show you later how this browser looks like and how some things in DICOM standards look like. To see how much DICOM is important, I will use the next slide to explain how a typical modern hospital today looks like from the perspective, from IT perspective. Contemporary hospitals today implement electronic medical and health records, and they have medical workflow management systems that are employed on a daily basis. Also, they use many different standards and technology systems. So as you can see on this slide, first there is health information system that manages and processes and supports clinical operations, medical data care activities, but also hospital business and administrative functions and similar. Also, there is a radiology information system that manages and processes all radiology departments' administrative, financial, and clinical data. And usually, information systems in hospitals exchange data between themselves by using HL7 or FAIR standard. And this is one part. Maybe the most important part of modern hospitals is the picture archiving and communication system, or the PAC system, which is a medical imaging technology for data storage and also easy access from different modalities. According to PACs, there are 4 different types of modalities. We have medical image acquisition devices like MRI, CT scanner, and similar. Then we have archive, where medical images are stored. We have next workstations, where radiologists and other practitioners can display, process, or interpret different images. And some of them can be outside of the hospital network, and they can access the PACs through the internet. At the end, we have a film printer for printing medical images. So all these modalities communicate between themselves by using some DICOM transport mechanism. So from one side, DICOM provides different transport mechanisms for communication and data exchange between the modalities and application running on these modalities. And from the other side, DICOM offers a way how medical images and related data can be represented, can be stored, processed, and displayed. About DICOM, DICOM has its own representation of the real world, in which each entity For example, patient, study, equipment, or image is defined by different attributes. And for that purpose, DICOM is using object-oriented abstract model definitions, models that are named information object definitions, or IOD. Each portion of information in IOD, which is connected with separate class of objects, is named information entity. One information entity can consist of one or more modules. And for example, a patient module will group together patient-related attributes like name, surname, age, gender, and similar. All attributes that exist in the DICOM world are defined in a special part of the standard, DICOM Data Dictionary, and they are all formatted according to 34 different value representation types, like textual, numerical, date, time, and similar. Another important term in DICOM is application entity, and this is any DICOM application that runs on any DICOM-enabled device. This term dataset is very important. An instance of the specific object is a dataset in which each attribute is represented by a data element. Each data element is uniquely determined by its data element tag, and you can see on this slide that besides data element tag, optionally in the data element we can have vir type, but also value length and one or more values of even number of bytes. One data set can be nested in another data set, and DICOM puts order in this in all of this by using this here. You don't see it. This here patient study series image hierarchy for data elements. This hierarchy means that one patient can have one or more studies. One study can have one or more image series, and one series can have one or more images. Data set can be stored in a special DICOM file format with a DCM extension, in which data set is preceded with file header, which consists of a file preamble, prefix, and file meta elements. DICOM also provides several different transport mechanisms for communication and data exchange between application entities. Here in this talk, I will speak about the DICOM message service and a little bit about upper layer service, but also there exists a DICOM web service AP and HTTP service, basic DICOM file service, and DICOM real-time communication. So one way how you can transfer a data set to another DICOM-enabled device is to put it inside the DICOM message from the DICOM message service or DIMS. Data set in the DICOM message is preceded with command set, which is a set of command elements. And if you compare these command elements with data elements, you can see that they are very similar. One difference is that instead of data element tag, we have a command element tag, and in this command element tag, the group number is always zeros. DICOM DIMS service usually is using in combination with the upper layer service, which allows communicating application entity to establish first associations, then to exchange different DIMS messages, and then to terminate the associations. Also, in all this process, a client-server model is used, and there are special names for clients, service class users, while servers are named as service class providers. All services in DIMS are confirmed, so we can see this on this example here with the most simple DIMS service, CECHO service, in which the DICOM client, in this case DICOM workstation, sent a CECHO request to the service class provider, the archive, and archive needs to respond to this with the CECHO response. On the right side, you can see command elements for both CECHO request and CECHO response DIMS messages. Also, each DIM service is associated with the data, actually with the IOD that is processed, and this is known as SOP or service object pair. So each SOP belongs to some SOP class. You can see on this slide, for example, that DIMS service restore can be applied to city image IOD, and together they form enhanced city image storage SOP class, which is part of special service class. This special service class is storage service class. So one or more subclasses which are related to a specific function, for example, with the storage of images, need to be they form a service class specification, and this is very important for device device conformance with the DICOM standard. What does this mean? Usually, each application entity that runs on some device does not implement entire DICOM standard. It implements only portion of the DICOM standard, only several functions that are needed, so it can perform his duties. So usually each application entity goes with DICOM conformance statement, which is a detailed description of all the DICOM specific functions that are implemented for that application entity. So the people that work with DICOM-enabled devices and application usually need to know these conformance statements. And if you look, for example, on the different conformance statements from two different devices, and if you understand this, you can see whether these two devices, these two application entities can communicate between themselves and to the what extent. So before I finish with DICOM, I want to share with you to see how this DICOM browser looks like. Sorry about this. Do you see this analytics browser? Can you see this browser? I suppose you are seeing it. This browser is made by Analytics, and here you can see different classes, how to say, different IODs that exist in the in DICOM. For example, if we look at city image, you can see different modules. For example, patient module is given here, and you can see different data elements like patient name, patient birth date, and similar. The image inside of this city image is you can find it here in image pixel. So if you click on this final part here, pixel data, is in fact the stream of pixels that from which the image is comprised. So I think this is enough about DICOM. So I will continue with the possible attacks. If you take any DICOM file and if you try to open it into any ordinary text editor, you can see that some parts of the file are readable. So, for example, I have here also example of this. You can see here, for example, that you can read the left knee or a report or something like that. And this is in fact this image opened into ordinary browser. So anybody can read textually attributes from the DICOM files in ordinary text editor. Not only it can read it, it can also modify it. There are two main unsecured DICOM services that run on ports 104 and 11,112. And if you try to send DICOM file on these ports, an attacker can intercept it and read it. And even an attacker can query the DICOM server behind these ports. One research study from 2016 showed that 2,782 unprotected DICOM servers are across the globe, and many of them are open to discovery of patient information. Also, another study from 2019, which was done by using Shodan platform, showed that there are 1,849 medical images and 842 PAC servers that they were exposed to the internet via unsecure or poorly configured web interface. In 2021, BIC showed that the DICOM images could be accessed and modified by attackers with basic skills or via standard tools and precoded scripts or exploits. He showed that open source implementation and cost-effective packs are especially vulnerable to this kind of attacks. Also, if even in the case where the hospital network is well protected from the outside world, if the attacker go into the hospital and if he tried to obtain the access to the hospital network, he can gain the access to the also different modalities that use DICOM standard. There are lots of research about how an attacker can auto remove the evidence of medical conditions from medical scans, and in that way he or she will change the diagnosis of the patient. So a healthy man can be operated, or a man with cancer would not be operated. These modifications are so good so that they even deceive experienced radiologists and state-of-the-art artificial intelligence screening tools. Also, there are other ways how to inject data into DICOM. For example, Ortiz demonstrated how one can hide executable code inside the DICOM file by using portable executable format. And in this way, he managed to obtain polyglot content, which means that this file from one side, if you are opening this file into the DICOM viewer, you can see it as a DICOM image, medical image, but if you try to run it from the operating system, it runs as an application. This is possible because of one little known feature of the DICOM file format of allowing unspecified preamble. So pixel data content can be shared with different file formats, for example, with TIFFs. So an attacker can put malicious code into the preamble, which is 128 bytes long. And in this way, this vulnerability can be exploited for hiding malicious code. This is known vulnerability of DICOM, and there are several ways how you can mitigate this vulnerability. One way is to fill the preamble with zeros, or other ways to check different parsers, DICOM parsers, to check for known preamble of different image format. Also, another way how to inject malicious code inside the DICOM file is coming from its support of encapsulation of other file formats into the DICOM file. Some types of files that can be incorporated inside the DICOM file is PDF or stereolithography or MTL and similar. And some of them have known and unknown vulnerabilities that can be used for injecting inside some malicious code. So in this way, an attacker can inject malicious code inside the carrier file format, for example, PDF, and after PDF is encapsulated into DICOM file becomes a carrier of the malware. Also, DICOM standard supports storage and transmission of compressed content. We have compressed video, images, audio, but also entire DICOM file can be compressed with the deflate algorithm. So, because of that, lots of vulnerabilities can rise from this use of compressed content. And one of them is the possibility to hide objects inside the compressed content, malicious code, and after decompressing to trigger the execution of the malicious code. In line with this, we also performed some research. We created three different scenarios in which we used two known zip bombs to attack DICOM web solutions and also DICOM viewers. And in each case, we obtain the crash of the DICOM viewer application or of the web application that was running on DICOM server. For those who do not know, zip bombs are usually small malicious archives that when some application try to decompress it, it extends to to large extent and usually use all resources on the system. Some of these zip bombs can be extended to 4.5 petabytes. This is no issue about zip bombs, but we tested here because still lots of antivirus software doesn't recognize them as a malicious file, and also it is easy to create similar zip bombs that another antivirus programs would also want to recognize. The only solution about this is the use of antivirus software. Our main research about DICOM was about the information hidden in DICOM, which can have illicit and legitimate application. And one reason is the recent deployment of a new type of malware, so-called stego malware, which deploys steganographic techniques in propagation and execution phase of its life cycle. We also suggest different ways how to one can create covert channels in DICOM, which are used for clandestine communication, and they can be created by three ways: by using text steganographic techniques in the textual attribute of DICOM file, by using digital media steganographic techniques in DICOM files in the medical images itself, and by using network steganographic techniques in different DICOM transport mechanisms. We suggested three different scenarios how these covert channels can be created. The first two scenarios are examples of direct covert channels where covert sender communicates directly with the covert receiver. And in the first scenario, covert sender uses the application entity of its device to send stego, for example, stego DICOM file or some message from the transport mechanism to the another receiving application entity from the stego receiver. In the second scenario, one or more covert receivers sniff the network and they can intercept the stego file or network messages, so they can conclude about the hidden, about the secret message. The third scenario is example of indirect covert channels in which the covert sender uses some innocent intermediate node, usually archive, so he can transfer the messages to the third party, to the covert receiver. Here I will present two different kinds of covert channels. One is with from text steganography. It uses Whitespaces in the textual attributes of the DICOM file, and another is from network steganography. It uses some services from DINSE transport mechanisms. The first covert channel is possible because values in data elements of the dataset must be of with length of even number of bytes, and because of that, it's normal to have more white spaces. And all textual attributes their types allows one or more white spaces at the end of the value. So one can create a unidirectional 1-bit covert channel by using this presence of 0 or 1 space character at the end of the data element will be binary 1. If there are 2 or 3 space characters, this will be binary 0. Also, there are 4 different textual where types that support also non-significant leading space. So additionally, one can create another unidirectional one with cover channel by putting additional white space at the beginning of the value. So the absence of the space character at the beginning of the value will be binary 1. And if we have, for example, 2 space characters at the beginning of the value, this is going to be binary 0. If we use, for example, CT computer tomography niche for hiding data, and if we use only mandatory textual attributes in this IOD, one can hide 113 bits per CT image. So the next cover channel is example of network steganography cover channel and example of indirect cover channels. And in this case, the cover sender and receiver are using CMOV and CSTOR services. Cover sender first creates a CMOV request, which is sent to the innocent archive as intermediate node. The cover sender hides the message into the 16 bits long message ID command element. And as you can, here are also given other command elements by which, in fact, the cover sender wants the specific DICOM files to be stored onto the targeted another third application entity. And here, remove destination, you can see the target application entity title. So when the archive received this as a service class provider, immediately creates a new CSTOR request to the target application entity title, in which now the archive is user and the target application entity is the provider. And in this request, message ID from CMOV request is copied into movie originator message ID. This is very simple, and in this way, these 16 bits are transferred to the target application entity. Also, in the same paper, we suggested use of entropy-based detection method for discovering of cover channels. Network cover channels created in DICOM, and this method behaves differently when the secret message is in plain form, ASCII, and behaves differently when it is AES encrypted. So this is enough about the attacks. I will continue now with the last part with security features which are built in DICOM. There is a special working group 14 that deals with security, and also there is a special part from DICOM standard, the 15th part, which is about security and system management profiles. First, you should understand that DICOM does not specify access control to data, and this is limited to the devices and to the applications. First, security feature which is built in DICOM is secure transmission over TLS, and DICOM suggests that clients and servers should support TLS version 1.2 and may support TLS version 1.3. In the specification of the standard, you can find all the cipher suites which are allowed, but also those which are not allowed, and there are also all specified key lengths for different algorithms. When TLS is used, the recommendation is to use the port 2762, which is a registered port for DICOM over TLS. Also, DICOM specify user credentialing with 2 options. One is using of mutual TLS authentication, and the other is assertion during association negotiation phase by using SAML or Kerberos. There exists also possibility for the digital signing of entire or partial DICOM objects or files, and for that purpose, suggestion is to use ERSA, and several hash functions are presented here. Also, there is a special part about security of DICOM files on media and on in emails. When there is a possibility for encapsulation of DICOM file into the secure DICOM file. And to do this, first the user must use ISO triple dash for content encryption, to use RSA or password-based encryption for the key derivation algorithm, and to use either ISO or triple dash for the key transport of the content encryption keys. DICOM also allows selective encryption, which means that you can encrypt not entire file, DICOM file, but also you can encrypt some subset of attributes or even one attribute. For secure email transport, there is a recommendation that the entire mail with the attachment should be encrypted with ICE and should be digitally signed by the sender. DICOM also offers the identification of attributes, but you need to be aware here that this does not guarantee that all individually identified information will be removed. So if you want to create some DICOM dataset, you should use this feature as part of the identification process, but you should also use some other tools. You can see there are lots of security features presented in the DICOM standard. The problem here is that the DICOM standard does not enforce security, it just provides it and recommends, but most of these recommendations are ignored by manufacturers and not implemented due to the difficult management and infrastructural complexity. So we have security, but most of the manufacturers doesn't use this when they deliver different devices and application entity, different application on different devices. So this is all about my talk. Thank you for the thank you for listening.
Thank you, Aleksandra. Thank you for your
So if you have any questions, I will stop the sharing.
I have not seen any question in the chat. I don't know if any of the attendees. Okay, just one. Okay, Neil, can you? I'm allowing you to speak.
Hi. Yeah, thank you for nice talk. Can you hear me?
Yes.
Yeah, so basically the chat is disabled, I think, so that's why it's not possible to write for participants any question there. So maybe I can ask here since I'm on mute. So my question is more related to this adaptation of DICOM format in pathology, because I see it's only limited to radiology for now and medical imaging. So what's your thoughts or opinion on that?
Is not only limited to radiology are the most the people that they use most DICOM, but PAC servers where DICOM imagers are placed is also work with DICOM. Modalities, workstation, DICOM viewers, they all work with DICOM. So maybe radiologists are the biggest user, but they are not the only one.
Also, one more thing about related to anonymization or the data security aspect that you described. It was not very clear like how adapting DICOM would try to totally eliminate the possibility of data breach or reconnection identity.
If you open, for example, part 15, you can find there are different security profiles, and one of the profiles is about the identification, and they have recommendation how this is going to be done with different things inside the DICOM. And if somebody wants to use this in the application entity, it must be in the conformance statement, put it that it supports this the identification profile. So everything is written in the part of the standard. They choose some, they select some of the, usually they select some of the textual attributes from the DICOM file, and they have way how to change them with, for example, John Doe or something like this, or clear them out. But there is no guarantee that you manage to clear out all the private information about the patient. You need to use something else also to check that the data identification process were finished completely.
Yeah, thank you.
Thank you, Neil, for the question.
Thanks a lot. I don't know if there are other questions. Or maybe in the meanwhile, I can have one just out of curiosity. Do you think in the near future there will be some modification in the standard to include some of the concerns you have highlighted?
This standard is constantly changing, and security of, especially the security part 15, is constantly changing. And includes more and more features, and some of the features became obsolete. But the problem is that different vendors does not implement it. That is the problem. So the security group is working. There are the features, security features, and somebody must implement it. It's not obligatory. That is the problem with DICOM security. Security features are not obligatory to be implemented.
Okay, thanks. Other questions from the audience? In case you can raise your hand. I do not see any additional question, so I would like to. Oh no, there is another one.
One last question. Yeah, one more question. Yeah. So she wrote in one of your slides like the DICOM standard in total comprises of 7,000 pages. Is it like the total standard or just a single document with this much big length to see or understand several aspects?
The sum of all 22 parts is more than 7,000 pages. So take into account, for example, if somebody wants to implement some parts of DICOM, it is very difficult to follow the standard. So because of that, there is that DICOM standard that I show, which can help to the developers, to the researchers, and similar. So for them to be more easily to implement DICOM standards into different applications.
And these 22 parts are like 22 versions, or it's like the combined explanation?
Yes, they work together also. Because security also has some part into the basic standard part in the 6th part, and also there are interconnection between all the working groups and all the parts.
All right, cool. Yeah, thank you for a nice talk.
Okay, thank you, Neil.
So I don't think there are other questions. And so, Aleksandra, thanks a lot for your interesting presentation, and thanks to the audience. I think that's it.
Okay, thank you everybody for listening.
Thank you everybody, and have a nice day. Bye, Aleksandra. Bye-bye.
Bye.